All right, let's get started with chapter 3.2, logarithmic functions and their graphs. So we're going to introduce the concept of the logarithm in this section. And so all the logarithm is if we don't know what the exponent is, the logarithm will get it for us. So here's how we set it up. If we say a to the y, and we don't know what the exponent is, but we know what the base is, and we know what the answer is, we can rewrite this as base to the answer is our exponent with a log in front of it here. All right? So if we have, just as an example, log base 10 to the 100, we could rewrite this as 10x equals 100. And then we would say, oh, x is going to be 2 because 10 squared is 100. All right, so our base, and then what our answer is. So let me write this out. Base, answer, if we're simplified, we're looking for the exponent. All right, so that's what we're up to here with logarithms. So let's take a look here. So first one here, 2 is our base, 32 is our answer. 2 to what gets me to 32? And we actually just did this on our warm-up in 3.1, and the answer here is 5, because 2 to the 5th is 32. Let's take a look at this one. 3 to what gets me to 1? Well, if I'm going to end up at 1, the exponent's 0, because remember, anything in the world to the 0 power turns into 1. I start at 4 and I end up at 2, so I must take the square root if I'm going from 4 to 2. And the way we write square roots is with fractional exponents, with the half. 4 to the 1/2, or the square root of 4, gives me 2. And same thing here, I want to start at 10 and end up at 1 over 100, so I'm flipping it over. It must be negative. And then how do I go from 10 to 100? 10 squared is 100, but since I'm flipping it over, it must be 10 to the negative 2. All right, so that's what we're up to here for our basic log problems. Your job is 23. And that is not in there. Let me pause this a second and put that in there for you. Apologize, didn't put that in. Hold on one second. All right, there we go. That's better. Try 23 here. Log base 2 to the 64. All right, so let's evaluate some common logs on our calculator. So log, if we don't see anything down here, it's going to be log base 10. All right, so the one on your calculator, find the log button on there, and you can punch in 10. So you're just going to hit log and then 10, punch it in there. 10 to what power gives me 10? The answer should be 1. All right. 10 to what power gives me a third? It turns out it's this irrational number, negative 0.477. Log to the 10 to 2.5, so what number 10 to the what gives me 2.5? 0.39. And 10 to what power gives me negative 2? Can't do that, right? Can't do that, because if we had 10 to the x giving me negative 2, there is no exponent that is going to create a negative in front of this. Negatives just make, if my x was negative, it would just be 1 over 10 to the something, right? So there's no way to turn that problem negative. So we can't get a negative number. Your turn, 29. See what you get. 3 decimal places. All right, some properties really quickly. If our answer is 0, if our answer is 1, the exponent must be 0, right? Because anything to the 0 power gives me 1. A to the 0 is 1. If I'm doing log a of a, the exponent must be 1. A to the first gives me a. If I'm doing log a to the x, and I get this, then I'm going to cancel it out and just be left with x. And I think a better way to look at this one is by looking at it like this. If I rewrote this thing right here, I would say a to some exponent gives me a to the x. And we know by the one-to-one function from 3.1 that our exponent here must just be then x. So the log base a and the a are going to cancel out. Same thing here, a and the log a will cancel out. And we're just going to be left with x. All right, so then on the last one here, if the bases are the same and our answers are different, we can cancel the log a's, one-to-one property again, and we're left with just x equals y. So if we were to simplify, log base 4 of 1, it's going to be 0, because 4 to the 0 gives me 1. Log base 7, root 7 to root 7, root 7 to the first gives me root 7, so my answer here is 1. And 6 to the log 6 of 20, the 6 and the log 6 are going to be canceled, and I'm just going to be left with 20. Okay? All right, use those properties, see if you can do problem 33. Moving right along, using the one-to-one property, same deal here. Our log 3's cancel, x equals 12. Our log base 10s are going to cancel. We're going to have 2x plus 1 equals 3x, and we can solve that. It's 1 equals x. And then log base 4 cancels. X squared minus 6 is 10. Bring the 6 over. X squared equals 16. So x equals plus or minus 4. Either one's going to work. Now note in this one the negative works because it's not the whole thing being negative. It's just what we're plugging in there being negative. Okay, so we can use a negative 4. All right, your turn on 85. See if you can figure out x. All right, so now we're going to move into some graphs here, and the graphs here should look fairly similar. They're the same as the exponent graphs, but they're reciprocal here. All right, so if we were to graph these, let me go ahead and grab the graphing calculator. We're going to put these up here. So in my y equals, we've got 2 to the x, and then on the next line, we've got log base 2 of x, and I'm going to have to introduce something. Some of yours might have a function on here where we can change the base. We don't, so we're going to have to do log x over log 2. And this is called the change of base formula. It's not in this section yet. In your textbook, these graphs are just given, but for me to actually graph it on the graphing calculator, I need to do this. It's your x and then the 2 in your second one here. And let me go ahead and graph this, and I'm going to need to change my window. That's not a very good window. Let's go negative 10 to 10, and negative 10 to 10. And there we go. You'll notice that this one has an asymptote. This first graph has an asymptote y equals 0. This one is the exact same thing, but its asymptote is x equals 0. It's not going to cross this line here. So it's symmetric about the line y equals x. Remember from our exponent graphs, we're always going to cross at 1. Well, we're also going to cross at 1, but on the other axis here. This is going to be 1, 0, where we're crossing here. All right, so the graphs are just mirrors of each other, mirrored across the line y equals x. All right, so if we were to sketch it, here it is right here. So on this one, 2 to the 0 power is 1, okay? And on here, 2 to what power gives me 1, right? So that's going to be 0. 2 to the 0 power gives you 1, so they're just reciprocals of each other. All right, so see if you can use what we just thought there to find the domain, the x-intercept, and our vertical asymptote of this right here, and then graph it. All right, so let's sketch the graph of this, identify the vertical asymptote. So the vertical asymptote of log base 10 of x is going to be the line x equals 0. We are not going to cross this line. We are going to have a point at 1, 0. Okay? And then the next one that we could do, because remember this is log base 10 of x, 10 to what gives me, if I plugged in 1, if I rewrote this as y, because this is equal to y, if I plugged in 1 for y, I'm going to get 10 over here, because 10 to the first power is 10. So this point right here would be 10, 1. So it's going to be very steep, and then it's going to start flattening out. It will never flatten out completely. It's going to keep going up and up and up forever. So the range is all real numbers. The domain here, x has got to be greater than 0. Okay? It can't equal 0 either, because there's no way for us to get an answer of 0. It can get very, very small, but not 0. All right, and so there we go. Vertical asymptote at x equals 0. All right, so same thing here on 43. See what you can do with this equation. All right, so let's talk about some shifts. Same logic going on in here. Log of x minus 1, we're going to shift right 1. So instead of hitting at 1, 0, now we're going to hit at 2, 0. Our asymptote used to be x equals 0. Now it's going to be x equals 1. We're just shifted over by 1. Okay? Same logic going on here about 2 plus log x. Right? We used to hit at 1, 0. Now we're just going to be shifted up by 2. We're going to hit at 1, 2. We're still going to have the same asymptote. We're not shifted sideways at all. So still same up and down. All right, so shifting works the exact same way as all the shifting we've done up to this point. All right, so see if you can match up 45 with one of these, A, B, C, D, E, or F. All right, so let's introduce the natural log. So natural log is ln, and that cancels out our natural base. So if we want to do log of a natural base e, we just write natural log. All right, so log of e is ln, natural log. Let's go ahead and take a look. Go ahead and plug these into your calculator. See if you can get natural log of 2, 0.3, negative 1. We're going to get these answers. And again, can't do logs of negative numbers. The domain is greater than 0. Okay, so we would get an error on that one. All right, so see if you can tell me what the natural log of 18.42 is. Check the back of the book. Make sure you get the right answer. All right, home stretch. Last couple of problems. Let's do our properties here for natural log. 1 over e is the same as e to the negative 1. Natural log and e cancel. We're left with negative 1. E and natural log here are going to cancel. We're left with 5. The natural log, if we end up with 1, the base must have been 0. Natural log of 1 is 0. Any log of 1 is 0. 0 divided by 3 is just 0. What happens to the natural log and e? They're going to cancel out. We're going to be left with just 1. 2 times 1 is just 2. We went quickly through those properties. Pause it if you need to, but if you're ready, try this problem. See if you can tell me what x equals without using a calculator. All right. Last one here, let's find the domains. Natural log of x minus 2. All right, the domain should be x is greater than 0. We're shifted to the right by 2. So now the domain is x is greater than 2, from 2 to infinity. All right, same thing here. 2 minus x must be greater than 0. If negative x is greater than negative 2, x must be less than 2. Remember, we're going to switch it around. Okay, so we can see that on here. We're going to go from negative infinity all the way up to 2. All right, and on the last one, x squared has to be greater than 0. All right, x squared is greater than 0. If we were to write this, we could square root this, and we'd end up with x is greater than 0, and x is less than 0, which means we can be everywhere, everywhere, everywhere except 0 itself. So x is not equal to 0, but it's okay everywhere else for our domain there on 10. All right, so back to this one. Graph this, find the domain, the x-intercept, the vertical asymptote of this shifted natural log graph. And home stretch, here we go. Students participating in a psych experiment attend several lectures on a subject, and then they were given an exam. Every month for a year after the exam, the students were retested to see how much the material they remembered. Interesting. Sounds like some classes that we might have taken. The average scores for the group are given by the human memory model, which is right here. 0 is less than t is less than or equal to 12, right? Because we're testing for a year in months. What was the average score on the original? T equals 0 exam. All right, so natural log of 1 is going to be 0, so we're going to start at 75. Okay, and then we can plug in 2 and 6 to figure out our scores as they go down. All right, so we're just plugging in numbers into t. I think you guys can do that. So you need to do the exact same thing on 97. Just plug some numbers into t, see how that works, and see if you can figure out the domain. If you can get that, you've got them all. If you got questions, we will talk about it in class tomorrow. Good luck.